In November 2025, interstellar comet 3I Atlas reappeared after passing behind the Sun, and new observations showed that it was more active than expected. One of the most notable contributions came from ESA's JUICE spacecraft.
3I Atlas just did something it wasn't supposed to do. A spacecraft that wasn't even looking for it accidentally captured images showing the comet flaring up with two distinct tails at the exact moment when it should have been calming down, and scientists are trying to figure out what's going on. This is ESA's JUICE probe, and it was on its way to Jupiter when it happened to point its camera at 3I Atlas just after the comet passed behind the Sun, and what it saw was activity spiking, when all the physics says it should be dropping off. And that's creating some pretty big questions about what this object actually is. So let's start with what JUICE captured, and why this activity spike is so strange. The spike, JUICE caught 3I Atlas getting weirdly active. Alright, grab a chair, because this is one of those moments where a mission built for one job accidentally stumbles into something much bigger. JUICE wasn't built to study comets, and it still caught 3I Atlas with two tails. And the reason this matters even more is because JUICE did not use a specialized comet camera to do it. It used a navigation camera, a tool designed to help the spacecraft orient itself and avoid trouble, not to deliver dramatic science images. On the surface, it's easy to say, okay, that's just a pretty comet photo, and move on. But that image is actually a warning sign because it shows that the comet's activity is increasing, not dying down, and that's where the real story begins. So let's start with the context that makes the timing important. In November 2025, 3I Atlas re-emerged from behind the Sun and became visible again. When it came back into view, it did not look calm or quiet. Instead, it showed increased activity, meaning it was releasing more material into space and appearing brighter than before. This on its own would not be shocking because comets often react to solar heating, but then this activity didn't immediately fade as the comet moved away. Instead, it appears to be continuing in stages, almost as if heat is still working its way deeper into the comet's interior. That kind of delayed response is exactly what scientists watch for, because it can reveal what a comet is made of and how it behaves under stress. And since 3I Atlas is an interstellar comet, meaning it formed somewhere else entirely, every change in behavior carries extra weight. Now, let's unpack the main event. JUICE captured 3I Atlas, showing a bright coma and two distinct tails. The coma is the fuzzy glowing cloud around the comet's nucleus, created when sunlight warms the surface and material starts escaping into space. The tails are where things become especially interesting, because they are made of different stuff and respond to different forces. One tail is the plasma tail, which is made of electrically charged gas and is shaped by the solar wind and the sun's magnetic fields. The other is the dust tail, made of solid particles released by outgassing, and it is shaped more by sunlight pressure and the comet's own path through space. Seeing both at the same time tells scientists that the comet is actively releasing both gas and dust, not just one or the other. Why does that matter to you as a viewer? Because it shows that the comet is not gently leaking material in a weak or fading way. It is actively shedding different kinds of material that react differently to the sun's environment. The plasma tail acts like a windsock for invisible space weather, showing how charged particles are being pushed and stretched by the sun. The dust tail, on the other hand, acts more like a trail of crumbs, marking where the comet has been and how much solid material it is losing. When both are clearly visible, it suggests the comet is interacting strongly with its surroundings, even at large distances from the sun. In simple terms, the comet's activity engine is still running. Turns out the real story isn't the photo itself, it's what the photo implies about the system behind it. Let's ground all of this with the observation details, because dates and distances are what keep this from turning into guesswork. The image released by ESA was taken on November 2nd, 2025. JUICE then made its closest approach to the comet 2 days later, which places the observation right at a moment when the spacecraft had a good viewing angle. Even then, JUICE was still roughly 66 million kilometers away from the comet. That distance matters because it means this was not a close flyby with extreme detail. The spacecraft was observing from very far away, yet it still picked up a bright coma and clear tail structure. If you think about that for a second, it tells you something important. A distant, low-resolution camera only sees that much structure if the object is genuinely active. This was not a faint smudge made dramatic by image processing. It was activity strong enough to stand out across tens of millions of kilometers. This brings us to why JUICE seeing this at all is such a big deal. JUICE is a Jupiter mission focused on icy moons, not on comets passing through the inner solar system. The image came from the spacecraft's NavCam, which is not designed for high-resolution scientific imaging. It is designed to help the spacecraft navigate safely, yet it still shows a bright coma and visible tail structure. That alone surprised the science team. Think of it this way: if a tool meant for rough guidance still picks up fine details, the thing it is observing must be doing something dramatic. As a simple way to put it, if a navigation camera picks up this much structure, the activity has to be strong enough to punch through a very blunt instrument. Now that's something worth taking seriously. Now comes the messy part, and this is where patience matters. What we are seeing right now is partial and delayed information. ESA has only downloaded 1/4 of the NavCam image so far. The full dataset from JUICE's observations will not arrive on Earth until February 2026, with the main window expected between February 18th and February 20th. But there's nothing suspicious about this delay. JUICE is currently using its high-gain antenna as a heat shield, which means it cannot transmit data at full speed. Because of that, it has to rely on a smaller medium-gain antenna, which sends data much more slowly. So where does that leave us, and how do we move forward without jumping to conclusions? For the rest of the video, we'll explain what JUICE saw, why February 2026 matters, and what 3I Atlas could reveal about interstellar history older than our solar system. What looks dramatic on screen isn't always what's happening in space, and the difference between the two is where this story really begins. The mechanism, why the comet looks like this, and why February is the real event. So before we let one dramatic image take over our brains, we need to recenter for a second to avoid falling into a classic trap. A single image is like a single economic chart, useful, but easy to misunderstand. It can look clean and convincing while hiding a bunch of messy choices underneath, like how long the camera exposed the shot, how much the image was processed, and what details were sharpened or smoothed to make the object easier to see. It can also hide the limits of the camera itself, because a navigation camera is not built to pull out tiny details the way a science camera is. And in this case, the biggest hidden issue is that we are not even looking at a full frame yet, because ESA only downloaded 1/4 of the navigation camera image. So yes, the photo is real and it's exciting, but it is not the final verdict. Now, let's talk about the two tails. The dust tail is made of tiny, solid particles, like powder and grit, that get released when the comet warms up and starts shedding material. Those particles get pushed by sunlight pressure, and they also lag behind the comet's path, which is why the dust tail often looks broader, smoother, and sometimes a little curved. It's not a laser beam, but more like a cloud trail that slowly spreads out. The plasma tail, on the other hand, is made of gas that gets electrically charged, meaning it turns into ions, and once that happens it starts reacting strongly to the solar wind and magnetic fields flowing out from the sun. Because those forces are strong and directional, the plasma tail often looks straighter, sharper, and more whipped into a line. This is why the tails can point in different directions, because they are responding to different forces, and it's like watching smoke and sand blow in two different directions from the same spot, where the source is the same but the physics is different. Here's why that difference matters so much for this story. When you see a comet with both a dust tail and a plasma tail, you are basically seeing two separate reports about the comet's activity, one from solids and one from gas. The dust tail says, "I am losing solid material right now," and the plasma tail says, "I am losing gas that is getting charged and dragged around by the sun's environment." If the dust tail looks strong and the plasma tail looks strong at the same time, that is a sign the comet is not just quietly fading out, because it is actively feeding both systems. It also tells scientists that the comet is interacting with the space environment in a way that we can measure, because plasma tails behave differently depending on solar wind conditions. So even though the picture feels like a simple snapshot, it is actually showing a relationship between the comet and the sun, almost like a tug of war, where different materials get pulled in different ways. And that's why people keep focusing on the two tails detail, because it's one of the clearest visual signs of ongoing activity we can recognize without needing a laboratory. Now, the bigger reason this matters is that the comet's activity state appears to have changed. The article explains that compared to earlier images from ESA's Mars Express and the ExoMars Trace Gas Orbiter taken in October 2025, the JUICE navigation camera image shows 3I Atlas in a more active state. We should be careful here and not overclaim, because more active does not automatically mean something impossible or unnatural. In simple terms, it means the coma looks brighter, more material seems to be escaping, and the tails appear clearer and more defined than before. This could happen for normal reasons, like different layers of the comet warming up at different times, or certain materials becoming active only after heat moves inward. It could also happen because the viewing angle and lighting conditions change, which can make tails look more dramatic or more subtle, even if the comet itself did not change much. But the key point is that multiple observations across different spacecraft are building a pattern, and the JUICE image is pointing toward the comet looking more energetic than it did in the earlier set of images. This is exactly why the next part of the story is so important, because the real science comes from the instrument stack that JUICE used during its observations. Basically, JUICE did not just take a navigation camera snapshot and leave it at that. Rather, it observed 3I Atlas using multiple science instruments, and those instruments can answer questions that a simple image cannot. Janus, the high-resolution optical camera, could show clearer structure in the coma and sharper tail features, and if there are jets or uneven outgassing patterns, it might help reveal them, assuming the geometry allows it. MAGIS, the imaging spectrometer, can look for spectral fingerprints, which is a simple way of saying it can detect what kinds of materials are present based on how they absorb or emit light. UVS, the ultraviolet imaging spectrograph, can pick up ultraviolet signatures of gas species and help show how solar radiation is affecting the comet's escaping gases. SWI, the sub-millimeter wave instrument, can provide deeper clues about gases and thermal behavior, which is often harder to see in normal visible images. And PEP, the particle environment package, can help measure particles and the comet's interaction with the solar environment, which ties directly into why the plasma tail behaves the way it does. So why does February 2026 matter so much, beyond just being a date on a calendar? Because it is the bottleneck that controls how fast this story can move from wow to we know. Essentially, JUICE is using its high-gain antenna as a heat shield, which means it cannot transmit data at full speed the way it normally would. Because of that, it must rely on a smaller medium-gain antenna, and that sends data much more slowly. The result is that the full dataset is expected to arrive in the window between February 18th and February 20th, 2026, rather than arriving quickly after the observation. This delay shapes public narratives in a very predictable way because partial images create speculation. People fill in gaps with their own theories, and the viral moment happens before the scientific conclusions are ready. The science does not move at the speed of social media, and in this case, it literally cannot, because the data is still traveling through a slow channel. To keep this grounded, let's end this section with a practical checklist, because this is how you separate normal comet behavior from genuinely strange signals without getting carried away. What would confirm normal comet behavior is a set of spectra showing typical comet volatiles, meaning common comet gases, along with dust signatures that match what we already know comets release. It would also look like consistency across instruments, where the optical results, ultraviolet results, and submillimeter results all point toward the same basic story, even if each instrument highlights different details. Normal behavior would also include tail dynamics that match known plasma and dust physics, meaning the dust tail responds like dust and the plasma tail responds like ionized gas, without contradictions. What would be unusual but still not aliens would be a composition that looks heavily unlike typical comets, such as strange ratios or odd abundances that suggest it formed in a very different environment. Another unusual sign would be activity that stays high when models expect it to drop, or repeating asymmetry patterns that suggest the comet has strong localized vents or structure driving outgassing in a consistent direction. What would be truly shocking, and we should say this carefully, would be signals that simply do not match dust and gas physics across multiple instruments, especially if those signals stay consistent after scientists rule out viewing geometry, processing choices, and camera limits. But the moment those February results arrive, we'll find out whether this is just another icy visitor or the first sign that this object is carrying rules from somewhere else entirely. The payoff. Why this comet could be a time capsule older than the solar system. Now, let's zoom out, because this is not just a story about a comet having a double tail for a few days and giving us a cool image to stare at. The real claim here is that 3I Atlas may be up to around 7 billion years old, and that changes the emotional weight of everything we're watching. Think about what that means in simple terms. Earth is not even close to that old, so this object may have formed long before Earth existed, in a time when our solar system was not even a plan yet. That makes it less like a normal comet and more like a drifting time capsule, carrying tiny pieces of chemistry from a different place and an older era. If you ever wished you could hold a rock from another part of the galaxy and ask, what was it like over there? This is basically the closest real-life version of that idea. The tails and the activity spike matter because they are not just effects. They are the comet leaking clues into space where our instruments can read them. This is the part of the story that usually gets overlooked, because the real drama is in how rarely we get the chance to observe something like this at all. In space science, timing and opportunity matter just as much as technology. We get rare observational windows and have limited chances to study interstellar material. And sometimes the most important discoveries happen with missions that were never meant to do this job. JUICE is a Jupiter mission, not a comet mission, yet it still ended up capturing something that could help answer very old questions. And that leads to the line that sums up why this moment matters so much. We didn't plan this observation, and that's exactly why it matters. It's a reminder that space science is full of accidents that turn into breakthroughs, because you can't schedule an interstellar visitor like a calendar event. When the universe hands you a surprise, you take the data you can get and you squeeze it for everything it's worth. If the incoming data is strong, scientists can learn far more than just this comet has two tails. The chemistry can hint at where the comet formed. The temperature history can reveal how cold or warmed it has been over time. And the balance between dust and gas can show how it releases material in stages. Put simply, this is the closest thing we have to a free sample from another neighborhood, because the comet is already leaking clues into space for our instruments to read. That's why interstellar objects change the game. They are rare, packed with information, and they test our models of how comets behave. And when the full data lands, we'll find out whether this was a normal outgassing surge or a hint that 3I Atlas is chemically different from anything we've measured before. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.